Hello. Let's see. Okay. So I configured the chat. Can you hear me? Thanks. That's great to hear. So can you hear me? Is actually test. Okay, that's nice. I wasn't sure. I somehow started the stream a bit differently this time. Yeah, so hello everyone. So in this so let me just open the stuff here. Hi. So in the last stream, yeah, we basically implemented model loading so that we have a plane here and a cube, and also did some shading. But if you look at this image here, for example, it's a bit hard to hello. It's a bit hard to see where the cube is located exactly. So yeah, this is why I want to implement shadows today. So then you have a bit of a better idea where the objects are located. As you can see, the cube isn't actually located on the ground. It's slightly above, which is not very obvious when you look at this image here, I think. So yeah. And also I wanted to So in the last streams, I always use the Xcode editor. And this time because I just used the raw Xcode editor without any features such as syntax completion or something, I wanted to try a different program which now lets me have auto completion. For example, if I type something here, I get a bunch of suggestions. And yeah, I just want to try it and see how it goes. Yeah. Please make a video on how you've learned all these things and your approach. Okay, so I will think about that. Basically, I just spent a really long time just experimenting with these things, and yeah. What do you exactly mean, your approach, physics simulation implementation? So before I start with the shadows, I wanted to add some explanations from the previous stream, because last time I talked about how to derive the diffuse lighting equation or the diffuse lighting model. And I wasn't really sure how to do this, but I looked it up, and so the way this works is we have a plane, and if you imagine that here is a light source, for my example like this here, and here is a light that shines light in this direction. So the way to work out how bright a point on the surface is, depending on how the angle of the light is, this works as follows. So we can look at the depth of the light cone, and in the shader we have, let me open the shader. Here. So in the shader we have the normal vector of the plane. So the plane is this here. And we have L, which is the vector that points in the direction of the light. So in this case, this would be this vector here. So, okay, you can't see it again. So the normal vector would be this here of this plane, and the light vector points in the direction of the light source. So it would be this vector here. And basically, we want to compute this length here based on this length here. So if for example this length here is A and this one is H, then you can imagine all of these light rays that hit the surface, when H becomes larger, then the amount of light that is hitting one specific point gets smaller. So the brightness of any point scales with the inverse of H. So that's just because when the light source hits the plane at a really steep angle, you can see that all of these light rays are now much further distributed, which is why this scales with the inverse of this length. So now the question is just how to compute h. And for that, you have to, so we can compute this angle here. This is the cos. So since n, the normal vector, and the L vector are normalized, this is just a cosine. This is just the dot product of n and L. But also this vector is the same as this. This angle is the same as this angle here. Because this here is a right triangle. And yeah, so basically these angles here are equal. So this is the same angle. And then you can, so if this was, for example, alpha, then you could see the cosine of alpha is equal to the adjacent divided by the hypotenuse. And if we rearrange this to h is basically, so we put h on the other side. And then we can divide by the cosine. So yeah, we can see that the length of this side here is equal to the length of this side here times the cosine of the angle, which in this case, because like I said, this angle here is the same as this one. This is the same as the dot product between n and L. And yeah, so what this means is h. Oh, I again forgot to. So I said the cosine. The cosine is of alpha is the same as this angle. So this is just a dot product between n and L. And this means that a scales with the inverse of the cosine of the angle. And this then means that the brightness just scales with the cosine of the angle. So that's just how to actually draw this diagram. And yeah, so that's why the diffuse lighting intensity in the vertex shader is this dot product here. So that when the angle between the normal vector and the light vector gets really steep, the light dims. Yeah. So that's just what I wanted to add to the last stream because I I wasn't really able to write this diagram down. And another thing that that a viewer told me was that so the lighting for the cube works here, but if we, for example, rotate the cube, for example, oh, let me get this a bit So the cube is rendered here. And the cube is rendered with this cube mat, which in this case is just a translation, which is also 0. But for example, if we rotate the cube around around any axis really, maybe the x-axis for example, and we use this angle variable because it gets updated each frame. So now I need to, this returns a 3x3 matrix, this is a 4 matrix, so I need to convert this. Oh, I forgot to. So now the cube rotates, but as you can see, the lighting doesn't update correctly. So basically the light source here is fixed. The light shines in a constant direction. I think, let's see, where's the light direction? Here, so this is the direction of the light. It points basically downwards and a bit in the X and Z direction. And as you can see, so the light should always be bright at the top here, but the lighting basically rotates with the cube, which is obviously not correct. And that's because we also need to transform the normal vectors in the shader. So basically we transform the positions of the cube with the model matrix, but the normals are not modified. And usually, since the normal vector, well, so if we have this cube here, and we have the normal vector of one side, basically when we translate the cube, so for example, if we move the origin of the cube to another position, we don't want to move the normal vector in the same way. So we don't want to move the normal vector so that it points in this direction. We just want to ignore the translation for the normal vectors. So this is why when transforming normal vectors, we usually ignore the translational part. So this is one reason why there is another matrix normally used in shaders, which is the normal matrix. So instead of M, it's the N. And this is a 3x3 matrix because we, like I just said, we don't need the translation. And for this, let's save this as well. So we just want to use the rotational part of the transformation. And yeah, so another one for the plane. But there's nothing interesting going on for the plane, so we can just set this to the identity matrix. I'm not sure if I have defined that. Well, okay. So yeah, and now we need to put these matrices into the shader as well. Render mesh, and besides the model matrix, we also pass in the normal matrix. And then we can pass this to the shader as well. Plane. So the only thing left now is to also transform the normal with this. And if we do that, there's an error. Oh, yeah, of course. So like I said, this is not a 4x4 matrix, so I also need to adjust this function call, because in OpenGL there's basically a function for every type you want to put into the shader. But now it should work. So now the normals get transformed too. And as you can see, the top part of the cube is lit, which is correct. And well, the bottom part is still dark. Yeah. But that's not all. So, because you need to be a bit careful when you choose what the normal matrix should be. So, as an example, so this is another example. If we had like this triangle here, wait, and you were to transform this triangle. So let's say this is the y-axis and this is the x-axis. If you were to scale this along the y-axis, then the triangle would look something like this. So this is basically the model matrix. But what happens if you transform the normal with the same matrix? Well, the normal gets scaled in the y direction too. And this looks like this. And this is wrong. So this is why, in general, you can't just use the 3x3 part of your model matrix and use it also as a normal matrix. So you have to be a bit careful. Hello for info. Yeah, so he asks how did I learn math? Basically in high school. And yeah, also in university, but it's not like I studied math or something. I just also had a bit of math. Yeah, and a lot is also from watching YouTube videos about like programming or specifically computer graphics. Yeah. Um, so yeah, so how to fix this? No problem. You are welcome to ask questions. So ideally, you would look at this and let's say you had your normal vector and the condition that the normal vector should always have is that for any vector inside of the surface, the normal vector and this vector here, so let's say this is the normal vector and this is some vector v, the condition here is that this should always be a right angle. So basically, the dot product between the normal vector and this vector here should be 0. And now we can think about what should happen if we transform this triangle, like for example here. So let's say the triangle is transformed with a matrix that is M. So M could, for example, just be the scale in y direction. Then the vector here would be scaled by M. And now the question is, we are seeking a matrix X with which we want to transform the normal vector such that the dot product is still 0. So such that the angle between the normal vector and the transformed normal vector and the transformed vector here is still 0. So with this equation here, we want to get a value for X. And yeah, so we can, the transpose of a matrix. So if we take the transpose of this matrix here, this is just the transpose of both of these, but in reverse order. So in this case, we have the normal vector, then multiplied with the transpose of X, and then with M times V, and this should still be 0. And what we can see is here is still the normal vector and V, just like before. Just we have now this matrix here in the middle. And yeah, so basically what this means is that this should be the identity matrix, because like here, there's nothing in between. So this must be like basically nothing. And nothing in terms of matrix multiplication is the identity matrix. So what we can get from this equation is that the identity matrix, or basically that this here must be the identity matrix. And with that, we can basically solve for X. So if we multiply this expression from the right with the inverse of M, we get that the transpose of X is equal to M inverse. So which means that just X is the M inverse and that transpose. And the same happens if you instead of looking at this expression, so if you swap the arguments, which is basically always possible for a dot product, if you were to do the same derivation here, you would end up with x is equal to m transposed and the inverse. So basically these two are equivalent. Okay, let's see. So hello Karim. What exactly do you mean? So basically you advanced way faster than the stream. Yeah, I mean, yeah, I know it's a bit slow, but I don't know. We'll see. So I can't really stream each weekend because I have a lot of stuff to do. But yeah. Okay. Yeah. So basically, if we have given a model matrix, we can compute the normal matrix, which is this here. So maybe I should have called this n. But to keep it consistent, let's call this x. So to compute the correct normal matrix, we invert the model matrix and transpose it, or we transpose it and then invert, which is the same. Yeah, so you have to keep this in mind when using the normal matrix. But for this simple example, it works. It still works correctly because the inverse of a rotation matrix is just its transpose, which means, well, that the inverse of the transpose of a rotation matrix is just the rotation matrix itself. Yeah. But in general, you would need to do this. Yeah, I think that should work. Yes, so in this case, it's just a rotation matrix. Like in general, the model matrix, this is so the last row is always like this. Here's the translation vector of the model matrix, and here is like the 3x3 part. And yeah, so to compute the normal matrix, you would just use this part here. So this 3x3 part, and yeah, invert it and transpose it. Hi, Lucas. Yeah, so I actually didn't start with the shadows just yet. So I basically corrected the normal transformation, which was still missing from the last stream. So now we have a correct normal transformation. And yeah, now we can actually go to the shadows. But maybe, so before we get to that, So if, for example, I would scale the cube. Okay, I just have a uniform scaling. But if I would scale the cube, I would now need to take this part here and basically apply this formula here, this one. Yes, today I want to do shadow mapping. Actually, I think so you could also, yeah, exactly. So the scaling of the scaling will also go in this 3x3 matrix. In the most general case, you could just take this 4x4 matrix, I think, and just like apply this formula here. So inverse and then transpose. And then, of course, you need a 4x4 vector because this is a 3x3 vector. And the last part is 0 because we don't want to include the translation. And if we take then the XYZ part of this should work as well. Yeah, so this works as well. But I don't know, so I don't think this is the most efficient way to do it because inverting a matrix in a shader, I don't know about that. So yeah. Of course, you could also just invert the model matrix here and transpose it and then extract the 3x3 part and use this. But I don't think I have an inverse function here right now. That's why I basically did this by hand. Yeah, so if you were to use this matrix here, we would have to now transpose these. So transposing means reversing the order. And transposing the scaling matrix does nothing because transposing because the scaling matrix is just the scaling matrix looks like this. And this here is all zeros. So transposing this does nothing. And transposing the rotation matrix basically inverts the rotation. So we would have to put a minus here. And then we have done the transpose, and now we'd have to do the inverse. Yeah, so this would mean we would have 10 here. And again, well, so first of all, inverting this would mean again, we have to reverse the order. Because for the inverse, it's also true that we have to reverse the order and invert both terms. So we reverse the order again. Now we would have to inverse the scaling, which is then, so the inverse of 0.1 is 10. And yeah, inverting the rotation matrix again is just removing the minus. So that's how you would do that, but yeah. What this means in terms of the triangle, because we invert the scale, basically, if we would take this normal vector and put it here, although this looks correct now, if I maybe draw a bit more of an extreme example, so we transform this into this one here. So the standard normal vector would be this here. The scaled like the model matrix would look like this. But the default normal vector is still incorrect because this is not 0. And this is why the inverse is here, if you want to have some kind of intuition for this. So basically, instead of scaling it in this direction, which is, for example, a factor of 10, we would scale this by a factor of 1 over 10, and then the normal vector would point roughly in the correct direction. I hope this just didn't make it more confusing, but so basically this is just a formula, and the way I think of it is we want to invert the scale, but we don't want to invert the rotation. So yeah, that's kind of the intuition I have, because the rotation is not destroyed by transposing and inverting, because that's the same operation for a rotation matrix. But for the scale, we invert the scale, and just transposing does nothing. Okay, so yeah, but now let's maybe get to the exciting part and talk about shadow mapping. So actually, so the idea is really simple. If we look at this scene here, because so a shadow is really, we have like an object here and the light source is here. And the shadow, let's say this is a directional light source, so it's basically infinitely far away. All light rays point in the same direction. So basically, the shadow is just caused by an obstruction of an object, which means that this surface is dark because this surface is lit. And yeah, so the basic idea of shadow mapping, if we don't do some kind of complicated ray tracing, is just we render the scene from the light's perspective. So for example, we would look at this scene from here. We would want to look at this scene from here and ask ourselves if this, so yeah, we want to see the scene with shadow. And for that, we render the scene from the perspective of the light, which is here. Because then we have like an image of just the lit stuff. So we would see this here, and everything we can't see is basically in shadow. So we can't see this from this perspective. We can't see this part, which is why it's dark. And just getting the color part is not really helpful in this case. So what we really want is the depth value. So we render the scene from this perspective just with the depth value. So we want to get a depth map. And because then we can say, for example, let's say here was a depth value of 0, and here was a depth value of 1. Then this part here, so the surface, of the sphere would have roughly a depth value of 0.5, for example. And this part here would have a depth value of 1. And then when we actually render the scene from the perspective we want to look at it, we can then see the depth values from the points we look at from the light's perspective. So we then look at this point, for example, and ask ourselves, okay, so this has a depth value of 1. And then we compare it to the render of the light space. And then we see that the same, so in the depth map, which is basically just a texture that stores the depth of each pixel, we then see that this point here has a depth value of 0.5. So this value has a greater depth value, which means that it must be in shadow. Yeah, so hello, Weevil. So yeah, so today I won't implement any papers, or I mean, I don't know if basic shadow mapping was published in some paper, but the plan for the future is to implement some computer graphics papers. But today I just want to implement shadows. Yeah, so to sum this up, we first render, well, we render the scene from light point of view. Hello, Pedro. So yeah, so it's basically just I don't really know if this has a name. I think it's just called shadow mapping. A good resource for this would be Learn OpenGL. So there are a lot of articles on how basically to do OpenGL rendering. And there's also there should also be a shadow mapping. Yeah, there's also, so you could look at this, or if you don't like text, there's also a bunch of YouTube tutorials. For example, I remember watching the ones by Thin Matrix. This guy. What about going? Yeah, so I first want to implement the basics. Is in the shadow camera, how do you gonna know the far plane? Yeah, so that's one of the problems with this approach. We have to just set some values. You can't really render something at infinity. So we basically have to say, okay, now here is the end of the shadow map. Yeah, so it's limited. This is unidirectional shadow mapping. Okay. Yeah, so I want to concentrate on the coding part now. So the first step is to render the scene from the light's perspective, and specifically the depth information. Yeah, and that's really the stuff I want to implement right now to start. But to do that, we so if you remember from the previous streams, to render the scene at all, we had to basically go through the transformation pipeline. So we had to set up a camera and a projection matrix, and this is like we have to do this as well here. So yeah, so first of all, we need basically the camera position of the of the of the light. So we have to specify, even though if the this like the sun is very far away, we just put the light source at some distance. Um, let's see. So if this here is the default coordinate system, basically the world coordinate system, then what I like to do is, because normally we are looking at the scene from this direction, so basically the camera would be here. I like to take this vector here and rotate it into the direction of the light by using like two angles, similar to how spherical coordinates work. Like first of all, I want to rotate this vector around the x-axis. So what I'm trying to do now is basically get the direction of the light at the same time as I'm getting the camera matrix for the light. So I want to transform the default light direction, which is then the view direction from the light's perspective, with this theta angle, and also around the y-axis with a phi angle. So let's write this into code. If we define these two angles here with some values. Then we can define a matrix that is basically the rotation of the light, and also at the same time like the camera matrix, like the coordinate system of the light, which is, so we first rotate by x. I can maybe, yeah. With the theta angle. And after that, we rotate around the rotation y light phi. Yeah, so this would basically be the equivalent of the camera matrix, which we had here. And at the same time, we can now compute the vector of the light by just taking the light rotation and multiplying it with the default view direction. So, like I said, we just built the camera matrix of the light system. So, and we look in this direction. And now if we rotate the light camera system, then this vector here, okay, let's see. So this is the direction in which we would look at if we would use this as a camera matrix. And because we want to render the scene from the perspective of the light, this is basically the same as the light direction. And yeah, so if we rotate this with the camera matrix of the light, then we also get the real light direction in world space. Yeah, and again, we can like define the view matrix, which is the inverse of the camera matrix, like before, by just inverting this matrix here. So basically swapping these arguments. And inverting the angles. So that's basically the view matrix. And the next part would be to make a projection matrix. And the thing here is, so the result that OpenGL wants us to have everything in, like this normalized device coordinate cube. This looked like this, so this was back here somewhere, I think. Yeah, so here, this is the NDC, whoa. This is the NDC cube. And we want to transform wait, let me draw in the borders. So this is -1, this is 1, this top one is 1, this is -1. And so in that direction, this is also -1 and this is +1. And for the projection of the light, because, so I want to implement a directional light, so every, the light direction is constant. So there is not a single light point, but there is like, you could imagine the light source is infinitely far away. Then the light rays would be all parallel to each other. And a projection matrix for this would be the orthogonal projection matrix. So basically, we just define a box which we then want to transform into this box. So the only difference between these two boxes is now that we define like a left, right, top, bottom, and because our coordinate system in world space is right-handed, the z-axis points in another direction. So we would have yeah, so the basic difference between the NDC cube and our projection box is just that we have different values for the edges. And yeah, so if we wanted to have a point light source that would point light, yeah, like from a point, then we would probably want to use a projection what's it, perspective projection matrix. So not orthogonal, so instead projection. But I want to use so parallel light rays. So I want to use orthogonal projection, which actually we haven't implemented. So here is just a perspective projection matrix. So yeah, we need to derive this as well, but fortunately it's not as complicated as the perspective projection matrix. So for example, if we look at the x value, so what we are trying to do is construct a matrix, the projection matrix, that transforms this box here into this box here. And yeah, so it's really just some scaling and some translation, nothing too complicated. So for example, if we look at the x value, if we have some point given, we could transform this into the range from -1 to 1. For example, now by subtracting L. So basically that x starts here. Then we divide by the range of these two, R minus L. So then we would have 0 here and 1 here. And then to transform this to -1 and 1, we can scale this by 2. Then we have 2 here. And lastly, we can subtract 1. Yeah, then we have -1 here and 1 here. And that's, for example, that's basically the transformation that is needed for the x value. It's not really that complicated. Hello, Twin Frozen. You're a 3D artist. I don't know. I just spent a bit of time experimenting with this stuff. Yeah, so to put this into a matrix, because that's not really a form we could put into a matrix, so we have to reorder this a little bit, because we want to separate the translation part and the scaling part. So for example, we could so basically we scale the x just by this factor here, which is 2 over L, R minus L. And the offset now, for the offset, we have to look at this value here and this one. And to put this into one fraction, we can, yeah, like make a fraction out of this with the same denominator. And then we have to, again, reorder the stuff and simplify. So because we have now the same denominator, we can put the numerators into the same fraction. And we see that here's 1L and here's minus 2L. So what's left is this just minus 1. And yeah, so that's basically the result. We could also distribute this minus into the denominator by changing the signs of these. But so that's what we would put into the matrix. So basically we had this projection matrix, the orthogonal. And the scaling factor of the x would be here. And the translation part, so here, then here comes 2 zeros. And the translation part comes here. And the transformation of the y is basically the same. The only and these here are 0, 0, 0, 1, just for like a 4x4 matrix. And now the only really a bit more difficult part is the Z transformation. In theory, it's exactly the same so it's really as complicated as the other ones, but the only problem is normally when you define these matrices, you define your near value and you want these values, your near and far values. For example, this could be 0.1 and this could be 100. So you want these values to be positive. But when you look at this here, you know, you look at this from this direction, which means that we look in this direction. But if these values were positive, this would mean that the near value would be further away than the far value, because this value is smaller than this one. So the only difference from the x and y edges is that we define this edge here to be minus far, or short form f, and this is minus n. Yeah, and this means that the derivation is a tiny bit different. Because instead of subtracting so we still subtract the lower part, but now the lower part is minus n. Yeah, so the lower part is minus n. So for the z value, we have to subtract the lower part, which means in the end that we just add the lower part. And then we have to divide by, again, the difference, so minus f minus near. Um, and wait, let's see. I need to think about this for a second. See, this is why I told you that the Z is a bit more complicated, because there's always this swapped I will just try this and then see if the result is correct. So we have this, and then we multiply it by -1, -2, because again we want to swap the order of these, because this points in this direction and this in this. And then we add 1, because we multiply this by -2. And let's see where we will get with this. So the scaling factor is -2 divided by n minus f. And then we have to look at this one, which is -2n n minus f. And then we add n minus f. So this means this is the scaling factor, and now we can add so we have -2n plus n minus f and divided by n minus f. And this is the same as this cancels again. So we have minus n plus f, n minus f, and then we can distribute the minus again. So I think this is correct. Okay, so let's just look at the solution. So this is the matrix I was looking for. Yeah, so it seems like I've made a mistake. Um, so I think the mistake was that I subtracted -1 from here, but the problem is that -1 is not smaller than -far, because -1, minus n, I mean minus n. Minus n is minus 0.1 and minus f is minus 100. So f is actually smaller than n. So to make this correct, I would need to subtract f instead of n. And the correct distance would then be probably minus n plus f, right? And then again, I have to swap the order. Okay, let's see. Sorry, this is probably a bit boring, but I wanted to get this right. So the scaling factor is again here, -2 f minus n. Let's see if this is correct. Yeah, this seems to be correct. This is the scaling factor. And then again, the translation, which is minus 2f f minus n plus f minus n f minus n. And again, this is the same as minus 2f plus n minus n, minus 2f plus f minus n this way. And then we can cancel this f. And we are left with minus f plus n f minus n. So let's see if that's correct. Yeah, this looks better. So the mistake I made was that minus f is actually the smaller of the two. So instead of, so let's delete this here because it's wrong. Because, so I have to subtract the smaller of the two values. Yeah, but that's basically, even though I made a mistake, that's the orthogonal projection matrix. So basically all these scaling factors are in the diagonal, and the translation factors, the translational values are in the translational part of the matrix. So yeah, we can implement this. I would just copy this here. And now we pass in the parameters of the box here. Where's the box here? This box. So left, right, top, or bottom, top, and then near and far. And yeah, so now we don't need this because that's from the perspective projection. We just need to implement these vectors, these values here. So for the x and y, the scaling factor is just 2 divided by the difference of the edge values. So the same for the y. In this case, it's top minus bottom. And the translational part is always this expression. Like here. And again, this would be bottom plus top divided by bottom minus top. And the scaling for the z was here. Why don't you just generate the code with Code Whisperer? What is this even? Is this some like ChatGPT or like Copilot? Lol. That's funny. Well, okay, why don't I do that? I mean, I like programming. So here we have far minus near. And this here is well, we can distribute the minus again. Far plus near divided by near minus far. Still coding manually. Yeah, guys. This is wrong too. Because we don't do perspective projection. Yeah, so that's the orthogonal matrix. It's the same as here. Just I put the minus in the bottom part. Yeah. Okay, so let's use this. So we have the view matrix of the light. It coded the snake game for me. No one cares about what. Hey, I mean, did it work? The snake. Okay, so snake. I mean, snake is kind of a simple game, no? I don't know. I like to understand how the things work, so that's why I like to sometimes do them myself. There's no, yes, there's no shadow mapping in the snake game. Okay. Yeah. Okay, so basically we now have the camera matrix. And what I want, so our scene looks like this. Here's the cube. And currently our camera matrix just lies somehow in the origin. And instead of offsetting this in some direction, what we can also do with this orthogonal projection matrix, because orthogonal projection matrices don't really care where they are originated, basically. What I like to do is just basically put the box just into the center, so we don't have to do this offsetting here. So this way so I don't need to do this offsetting stuff. I think that's a bit easier. So the only thing I need to do here to create a light projection matrix is just call this orthogonal and like define an edge size. For example, well, maybe 20 or something. And then I just say that the box should be, I guess it's the halved edge size. I can just put this into everything. Well, of course, left must be smaller than right. And the near value should also be smaller than the far value. So that's basically how to create this. When creating the orthogonal projection matrix, I would think it would be better to specify yeah, so that's what we actually did for the projection matrix. Wait. At some point, we also have to clean up this code because I don't know. So that's what we did for the perspective projection matrix, because for this matrix, you have like a cone in which, or like a pyramid with which has no top. And then it makes sense to define these angles, like the field of view y. I think it's this actually. But for the orthogonal matrix, we just have this box here. So we don't really have an angle. That's why we use these simple values. You can also define the perspective projection with left, right, near, and top. But yeah, that's even more complicated. I think this works fine. Okay. So now that we have basically the two matrices we need, we have the math part, but now we need to do the OpenGL part. So what we can also define like the transformation of both of these, because we don't need them independently. Oops. And so now comes the OpenGL part. And yeah, so for that, we don't want to render the scene from the light's perspective in the in the window, because we don't actually want to see the scene from the light's perspective. So we need to render the scene into an off-screen buffer. And for this, we can use frame buffers. So basically, there are these frame buffers. And yeah, so basically you create a frame buffer. So let's just do this while talking about it. Where, so maybe here. These are just like GLU and just like the other objects in OpenGL, these are defined by like a GLU and handle. And the frame buffer object is, yeah, it's kind of like a collection of images where you can render into. And they have attachment points. So I think they even had some. Here they had a pseudo implementation where they basically express in code what a frame buffer actually is. I think this is this makes it a bit easier to understand what these things actually are. So you have in a frame buffer you have these buffers, and I mean I'm not an OpenGL expert or something, but it's like a collection of images in which you can render into. And in our case, we are actually not interested in any color buffer. We only want a depth buffer. So yeah, maybe let's start with the creation of one of these buffers. So like every other object, we need to call this such a function here to create our object. We only want one. And yeah, again, we have to bind this one to modify it, because OpenGL is like this giant state thing. And I don't really know why, but I mean, what other targets are there? Okay. So it seems like you can specify different ones for reading and drawing, but we want to do both. So, well, I think it, so let's just use this one and then bind this. And now somehow these frame buffer objects, they are like default initialized with these GL color attachment zeros. So when you do nothing with the frame buffer, I think you have these default color attachments here. So it says like we have a color attachment, but we don't want this. we just want to have a depth buffer. So this is why we specify that with these commands here, gl draw buffer, that we don't have like any color attachments, and the same one goes for the read buffer. So I think this basically sets these to none. And yeah, so now we just need to put a depth buffer here. So in these attachment points of the frame buffer, you can put images, textures, render buffers. There's different types. So when you use a texture, you want to, you give it like a handle to the texture you want to write into. And so this way you can access the texture. As far as I understand, a render buffer you would use if you like want to render something, but you don't really care. You don't want to access the stuff that is written into the buffer. So here it says you can't access them in the shader. But we want to access the depth buffer, the depth buffer in a shader, so we use a texture. And the way you specify this is by calling something gl frame buffer texture. If I could spell. So, and the depth buffer is 2-dimensional, so we will use this function here. So for the first one, so gl frame buffer texture 2D. And again, we use our bound frame buffer, which is the target. And this attachment. So now we need to specify the attachment point. And let's see the attachment point here. So here are the different attachment points we can use. And we want to use a depth attachment. So we put this constant here. And then wait, the next parameter is the texture target. We just want to use a plain texture. So we would use, where is it? I think it's, so it's just the 2D texture without any multi-sampling or something. And the next parameter is the texture itself. So we haven't created the texture. That's what we have to do too. So this would be the handle to the texture. And then lastly, the level is probably the mid-map level. So we don't want to create mid-map, so I will just put the 0 level in it. Yeah, so that's basically how to create this frame buffer object. So we said we don't want to draw any colors. we only want to draw into the depth buffer. And now we need to create this texture. So GLGen textures. And again, we have to bind this one. And now this is the same as here. So this is the target of the texture. We don't want to pass the reference, the pointer. And now we need to use this GL text image 2D, where we define what the texture looks like, or what is inside of the texture, basically. So first, again, okay, so wait, I forgot GL check. So now we need to call this GL text image 2D. And the target is again this stuff we have bound. The first one is the level. So if you program something like this, I would really advise you to follow a tutorial or like look at the documentation, because I don't know, I can't really remember the stuff. I don't know if anyone actually can. I always forget the stuff. So specifies the level of detail. Okay, so we don't have mid map again, so I put 0 here. And now comes the interesting stuff. So internal format. Now we have to specify what the format of the texture would be. Internal format. And for that, we can just use one of these base internal formats. For example, this depth component, because we want to store depth values. It says here must be one of the, or it says can be one of the base internal formats of table 1. So we want to store depth. And the next thing, we need to specify width and height. So let's just define depth text size, for example, and set this to 1024. I don't think they have to be powers of 2, but I don't know, I just like this. So we can, so the texture doesn't need to be like the same dimension as the image. What this should be the same dimension as basically your cube with which you look at the scene. So if you look at the scene from here, this should basically be the same aspect ratio as the stuff you put in there. But I don't even think it has to be like that. So yeah, you can I mean, you can experiment with this stuff, but I think it makes sense to make it the same size as the box you are looking at. Then the pixels will have like a square size. The next stuff is border. Okay, so it says the value must be 0. And now you need to, so because you can actually specify data that is in the texture from the start, and then you have to specify what format the data is in and what type the data is. But I mean, we can pick like GL depth component here, but I'm not sure. I don't think this actually matters because we don't put any data in there. So the type is then GL float, for example. But so here we put a 0 pointer, which basically means we don't pass any data. So I'm not sure if this actually matters, but yeah, whoops. So like this, and for some reason, and this is something I don't understand as well. So you have to specify these text parameters, GL text parameter, where you basically say something like how the texture should be sampled. So for example, if this is your texture, which is 2 by 2 now, and you sample at a position that is here, you can specify if it should just take the nearest color value, because of course there are only colors stored at these positions here. Or for example, if it should use a bilinear interpolation. So that's, for example, what you can do with these texture filters, I think. Yes. And so it says here, at some point I read part of this stuff, and it says that these have default values, but it seems like you still have to specify some of them, which I don't really understand. But otherwise it doesn't work. So we have to specify the text parameter I value of the filtering. So we have to specify the GL min filter. So this is basically minification and magnification. So what happens when you have like, this is your pixel and your texture, which is like, for example, 4 by 4 or something, is like this. What color should the pixel be if the texture is basically in the pixel? Because it's not really clear what color you should pick now. And the other one is if your pixel is here and your texture is in the background here. And then you have to specify, well, which of the colors here you want to use. I don't know which one is minification and magnification, but these two filters basically mean how to sample the texture. And because this is a depth texture, we don't want to mix any depth values because that makes no sense. So for example, if we imagine we had a cube here, and way in the background there would be a plane. And now if we imagine that our texture would be like this, we don't want, when filtering, so for example, if we request, so here is a value that is, for example, 1, and here's a value that is 0.5. If we sample the texture at this position, we don't want to mix these two values because the cube doesn't reach to the surface. And so basically, I don't know if this is understandable, but basically interpolating the depth values makes no sense because the cube doesn't really extend to the surface. So if we look at this from another perspective, it could look, for example, look like this. So here at these positions, there would be no depth value, so it makes no sense to interpolate this range. Which is why we put the filter to, I think it's GL linear. So that it just picks, no, it's not linear, it's nearest. So it just picks the nearest pixel instead of doing some interpolations. Linear would be if you want to do interpolations. So, and then magnification. And yeah, so that's about it. So we can unbind the texture. Wait. Here to avoid making some errors. And we can also unbind the frame buffer here. And yeah, that's basically how to create the frame buffer. So the only thing we need to do now is render into the frame buffer. And to do that, we again have to bind the frame buffer. And we have to clear the texture. Basically, we have to clear the depth values. And another thing, so let's move this, which is basically the stuff for our actual draw call. Move this down here. Now we also have to modify the viewport. So we want the viewport is basically the region in which we, so I actually don't remember if I explained that, but you have your NDC coordinates, -1, 1, 1, -1, and your viewport is like another transformation in the transformation pipeline. This basically just scales this coordinate system into the window, which of course has like a coordinate system of, well, I don't actually know if it starts here. But basically the window coordinates is of course the pixel coordinates. So this here is width and this here is 0. And now I'm not sure if this is 0 and this is height, or if this is 0 and this is height. But yeah, it does something like this. So it basically maps these two positions here to 0 and width, and the y as well. So, and with this viewport, you specify this transformation. So basically you say, okay, you start at, you map these to 0 and 0, the lower bounds, and the upper bounds, you map these to the width and the height. And of course, because we render into the depth texture, which has a size of depth text size, we want this to be the size of the viewport. Yeah, and now we could actually already draw our let's move these up here. We could draw the scene. Into the light FBO. The only problem is we don't have the correct shaders. So yeah, we also need to quickly create some basic shaders. But before that, after we rendered the light stuff, we need to unbind the frame buffer, which basically means we want to use the window frame buffer. So binding 0 frame buffer means binding the window frame buffer. And then we have to, I don't know, GL report. GL viewport. Okay. So after that, we of course want to restore the original viewport, because now we actually, after we rendered the depth texture, we want to render into the window again. So now we need to specify, I think I defined these up here. Yeah, window width and window height. Window height. Yeah. So that should be it. Now the only part that is left is creating the light space shaders. But fortunately, they are really simple. This is running still. So we can just create, for example, a light vertex shader and a fragment vertex shader. And yeah, so the nice thing is we can copy these and remove a bunch of stuff. So this was the default fragment shader, vertex shader, and so we still accept the same arguments, but we don't really need to output anything. But this will be clear in a second. So the only thing we need to do is, so in the code we defined our, we had a single projection and view matrix. So let's change this here too. And we also don't need to transform normals because we don't want to do shading in light space. When we render the scene into the depth buffer, into the light depth buffer, we are only interested in the depth value. So we don't need anything besides positional information. So this is not needed. This is not needed. And yeah, that's really the only thing that's left. So we take our input point, transform it like previously. And yeah, then we apply the light and view, and projection matrices, and pass this thing to the fragment shader. And the fragment shader is now even simpler. Where's the, here? Because the fragment shader, wait, why does it, I don't know. So in the fragment shader, we basically do nothing. This is what the fragment shader looks like. We don't output a color because we don't specify the color buffer. We only want to output a depth value, but that's what OpenGL does automatically. We don't need to do that. So this is just empty. And yeah, this is just a point transformation. So let's see, we create the previous shader here. So let's create another one and call it light shader. Yeah. And then we need to bind the light shader. For example, here. So when rendering the scene from the light's perspective, we want to use the light shader. The only problem now is that yeah. Oh, okay. So I have the shader already here. So this should work. I just have to pass in the correct shader so that it sets the model matrix correctly. The only thing, the only uniform variable that's left is this matrix here. So I set this, for example, here, light PV, match PV, and this is light PV matrix. And I think this should work. I mean, we will not see anything because we haven't done anything with the depth map yet. Oh, okay, I can remove this light direction here because we now have another one. So, and hopefully we don't get any errors. Okay. So, of course, like I said, we still don't see anything because we now have the depth texture, but we don't do anything with it. So maybe we'll just try to actually use the shader, the texture. And for that, because so the light stuff is done, now we need to use the light map in the default fragment shader. So because here is where the actual lighting happens. So in this shader, we compute the light intensity and the shading of the actual result we see on the screen. So this is also where the computation of like the checking if the pixel is in shadow must happen. Yeah, and for that we need a uniform. And the textures have a special type in GLSL. So in this case, we have a sampler 2D. So this is what these textures are called in the shader. And yeah, for example, we name this light depth text. And yeah, now we need to bind the texture. So like I said, we are done with the light space rendering. What we need to do now is bind the texture into the second step. So we can do this here, for example. And basically we want to bind a value to this variable here. So again, we can use So GL check, GL uniform 1i, I think. So basically we just want to, so and that's a bit of a, well, I guess it's not weird, but we don't bind the, so we have our handle, the GL, what's it called? Depth text. So that's the handle of our texture. But we don't pass this directly. We don't pass this directly into here because that wouldn't work. In OpenGL, when using textures, there are basically a few slots. So let me draw this maybe. So basically we have these texture slots. So slot 0, slot 1, slot 2, slot 3, slot 4. And in these slots, we can bind an actual texture. So in a slot, we can bind our depth texture. And then we tell the sampler in which slot to look at. So the sampler should look in slot 0, for example. So this is why we will put a 0 here. And now we need to bind the texture into slot 0. And for that, we need to call GL active texture. So we activate a certain slot. And in this slot, we now can bind the texture. Yeah, so that's how to bind the texture. And if you wanted to use a different slot, there are these constants. So for example, you could also use 1 or 2 or 3. So if we wanted to use slot 3, we would then also have to put a 3 in here. Or you could just add a constant to this. So this here would now be slot 4. And then we had to put for slot in here, for slot 4 in here. But I will just leave this at 0. And now comes the exciting part. Because we can now maybe like check if we rendered the depth map correctly. So in GLSL there's this GL frag called there's this variable and it contains the position of the fragment or of the pixel we are looking at in this shader in window space coordinates. So what I will just try is, I want to see if I rendered the texture correctly. So this, and so, okay, texture, to sample a texture, we use this function. Basically you put the sampler, G-sampler. So we put the sampler in here. And then we put the position we want to sample at. And in this case, I just want to check, I want to see anything. I want to check if I did the – rendering correctly. So I will use this here. and just divide it by 1000 because it's in Windows-based coordinates, and textures have this coordinate system where here is 0, 0 and here is 1, 1. I just want to see if I rendered anything, and this will always return a vector, so I just want to get the first value. So because we only have like a depth, we only have one value, so I just want to get this one value. And I think yeah, so I hope this works. Wait. So let's see. I'm not actually. So wait. I think this is a bad sign. um. So the screen is white. What I expected was something like, well, anything other than white, because if we render the scene from the light's perspective, we should see at least some gradient, because like well, if you look at this scene from this perspective here, for example, well, this distance here is smaller than this one, so there should be a gradient here, like a depth gradient. And we should also see a kind of a cube. But unfortunately, we don't see it. That's really sad. Well, now I need to do some debugging. So wait. No, I changed these. Okay. So I need to think a little bit right now what I could have done wrong. So GL clear. So maybe you can look at if the texture sampling worked. So right now I am clearing the texture with the default, like the furthest depth that is possible, and the default value for this is 1. So just like clear color, where I specify what color is put into the color buffer, I can also specify the depth that is going to be cleared. So if I put 0 in here, we should see like a black screen. And actually we see nothing, which is really interesting. Oh, well, probably because the rendering itself doesn't work then. Yeah, okay, so the sampling itself seems to work because, well, if I clear this with 0, then we also see 0. So the texture sampling works. Maybe I can also check 0.5 just to be safe. Yeah, so now we see 0.5 here. So, okay. What else could there be wrong? Render doc. This is like where you can debug the stuff. I mean, that would certainly be very nice, but I have no clue how to set this stuff up, so yeah. Yeah, that would be really nice right now, but let's figure this out. Wait. Is this wrong? So it was definitely wrong. I don't know if this makes any difference. Okay, so now we see something. I'm just not sure what this is because, oh wait. Okay, so that was the mistake. So as you can see, now we have, well, I mean, I don't know why this is. It's probably not aligned because this is actually just a hack, but so at least we can now see the depth texture. So the mistake was that I put this shader, which gets the, well, actually I don't know what it returns because this doesn't even exist in the other shader. So this here, I don't know why this isn't an error, but okay, well, it works now. So yeah. So that was actually the most complicated part about all of this, because I don't know, you can make so many mistakes here. But now we know that we actually have the correct texture. The only thing we need to do right now is, and this is like the specifics of how this even works. So now we have like we have the depth texture here, and this was rendered from this from this point of view. So basically, this is the texture, and we have this cube now, and in our when we actually render the stuff from the perspective we see in the window, like for example from here, what we will do, not so we will have the default transformation that we have with our camera of the actual matrix for the window. But what we will also do, we will use the same transformation that we did in the light shader. So we need the light projection and view matrix. And what we will do with this is we will transform the point like here, but now with the light stuff, so light PV. And then we have a light point. That's basically the point projected into the light space. So basically, for example, we have this point here. And besides projecting it like normally for the render of this perspective, we also project it into the light space. So that means we project it like if this was the coordinate system. I mean, it's kind of like that. We also get the value like from here. And this way, even though we are in this perspective right now, we also get the depth of this point from this perspective here. And this way, because we know what's the nearest depth from this perspective, because that's here, we just rendered this, we know that the closest point, the closest visible point from the light's perspective is this point here. And this way we know, basically we check the depth of this with the depth in the texture, and then we know that this here is actually in shadow, because this here is well, if this is depth 0 and this is depth 1, because this here is smaller than our depth from the pixel. And that's basically how this works. So we have the light point, and now we need to output this into the fragment shader. Light P. I think, yeah, I need to remove this because it's defined up here. And now we can accept this in the fragment shader. So this is, we are now in the fragment shader, meaning we look at each pixel, and we have the position of the point in the light space. So what we now need to do is compare the depth here in here with the depth in the texture. And because this is a 4 by, so this is a vector 4, so I don't think actually this matters here, but ideally we would need to divide this by the W coordinate. Because if we had some kind of perspective projection, we had to de-homogenize this point. So when we put our actual point into this GL position, the division by W is actually done by OpenGL. But since we now pass this point manually to the fragment shader, we need to do this manually too. And this way we have our light point XYZ, the actual XYZ coordinate. And now we want to, so first of all, we want to use this 1 to get the depth of the point in light space. And 2, we want to use this point to sample the depth from the texture. So because the texture space, so how to sample a texture, like I said, the coordinate system of how to sample a texture looks like this. So here is 0, 0, and here is 1, 1. But this point here is basically in NDC coordinates because we just did the projections. So what this point is defined in is this here. -1, -1, 1, 1. So, so this is texture. And this is NDC. And this is what we have, and we want to convert to this one. So what we can do is just add 1 to get 0 here, and then we have 2, 2 here, and then we can divide by 2. So we can do this with the point light XYZ equals like first add 1, and this works because, well, this is built into GLSL. It will just add 1 to each of the components. And then we can divide by 2, which also divides each of the components. And yeah, so this is now, we can use the X and Y values. They are now mapped to 0, 0, and 1, 1. So we can already sample this. So, well, maybe like closest depth or something, closest. And this is like just, we sample the texture. At this XY position, .xy. And of course, we just want the first value because there's only one value stored. So this is the closest depth we have stored in the texture. And the depth of the point itself, we can, we can use exactly like this too. Because, and this is actually one of the errors I made in the first devlog video, what I talked about. So, because the NDC depth looks like this. So the NDC cube. The NDC depth is of course still -1, 1. Again, I don't remember if this is -1 or this is -1, but it's in the range from -1 to 1. But the actual depth buffer stored depth is a different range, and you can specify this with the GL depth range. And this is how, so here, specify the mapping of depth values from normalized device coordinates, so NDC, to window coordinates. Okay, so this is like the depth in the window coordinates. So basically, this is the missing function to the GL viewport function, right? And here the default value is 0 and the other value is 1. So what we have, the depth in the texture is in the range from 0 to 1 if we look in this direction. And now that I think about this, this is also, so the -1 is here and the 1 is here. So these get mapped like this. And actually, that's the same mapping we did for the texture space by using this command here. So we can just use the actual depth. Or what should I call this? Point depth. And that's just the Z value now, because we transformed this to 0 and 1, which is the depth range here. The default depth range. If you change this, you also need to account for this, but like I said, we have the default values. And yeah, so now we have the depth of our point in light space and the closest depth in light space. And now we can determine if the point we are rendering is actually in shadow. Yeah, so if we look at the diagram again, if our point has a greater depth value than the stored, then we have shadow. Whoa. So we can define like shadow factor. And if the point depth is greater than the closest depth, we have shadow, so we want to multiply by 0, and else we have 1, we have no shadow. And I think this could already work. Let's see if I made a mistake. Yes. Okay, so light P. Okay. And it didn't work. Because I didn't, okay, so I forgot to set this matrix. So of course I need to set this matrix in the other shader too. So in the actual shader now. Light PV. And for this, I need to use this matrix. Second try. Okay, so now it works, as you can see. Well, kind of. Yeah, so it actually works, but this is a problem that's called shadow acne. And basically what's happening here, yeah, I mean, it actually looks kind of cool. I don't know if the if the compression destroys this, but I don't know, it looks kind of cool. So what has happened? So in theory, it works. So we implemented what we wanted to implement. So we have shadow here, and I mean, this is kind of lit. Well, let me draw what's happening. So basically, we have our ground, and now we render this ground into this texture here. So we look, wait, you don't see it exactly. So we look from this direction here. Yeah. Yeah, true. That's also, you can see that in the stream. Interesting. So this here is shadow acne. I think that's how it's spelled. And the reason why this happens is we look at this, we look at our object, and we render it into this texture here. And if we map the pixels, so basically, if our texture was like, if this was 1 pixel of our texture, we have to map these pixels here. So what is happening? This pixel, if we look at this pixel, for example, what is stored in this pixel? The pixel stores the depth value, like it has to store some depth values, because actually all of these depth values are different. As you can see, if we draw this like here, this would be like one depth value. But as you can see, these are all slightly moved. So if you were to look at the depth values of each of these positions here, they would all be slightly different. But the pixel just stores one depth value, like this here in the middle. So what is happening now, if we render the scene from another point of view, so for example, if we render the scene from this point of view, we would see that this depth value at this point here is actually shorter, so it has a smaller depth, and this pixel here has actually a larger depth. So what is happening? This pixel is in shadow, and this pixel here, like I mean pixel from this point of view, this pixel here is in light. So because the resolution of the texture is limited, we have some sort of self-shadowing, because the texture only stores the like the average depth value. We have if the resolution of our actual point of view is way higher than the resolution of the depth map, then we have, for example, a pixel here, and a pixel here, and this pixel here is like it has a greater depth than the stored pixel, even though it is in the same light texel. And this is why this is in shadow. However, on the other side, this has a shorter depth, and it's in light. So this is why we can see, if we look at this, we can always see well, maybe I should remove the cube to make this a bit more. Let's remove the cube. So you can see here, well, we can see here we have always these Well, like these lines where we have shadow, no shadow, shadow, no shadow, and this is exactly what like here in the image. So again, this here would store this depth value. So this point here again would be in light because it compares against this texel, and this here would again be in shadow because it again compares against the same pixel. So we then have these repeating patterns, which are very ugly. And to fix this, some people just use like an offset. So when they sample this, for example, they increase the length of the texel that we that is stored by a bit, so that everything on this depth range would be in light. But I mean, I don't really like this because if you would have a very steep light angle, so for example, if the texture was like this, then your pixels you would have this huge range, and you would have to use a very large offset for this to work. So I don't know. I don't really know why so many people, or like the guy on Learn OpenGL uses this, or I mean, technically he just explains this. But there is, in my opinion, there's a way better solution, which is to just draw wait to just draw the back faces of each of the models when rendering the lights perspective, because shadow acne only occurs, wait, I just closed this, because shadow acne only occurs on the part that is actually lit, and let's re-enable the cube again. So wait, let me write this down quickly. So when rendering the light, we will I think cull phase is already enabled. No? Okay. So first of all, we have to enable phase culling, which basically wait, what? Which basically enables us to discard or not render parts of the model depending on the triangle winding order. So for example, if we have this triangle here, this is a front face because it is it points counterclockwise, but this here is a back face because it points clockwise. And when we render a model, these are always specified, or if you did it right, they are always specified such that when looking at the front side, these here are always counterclockwise, and the back faces are always counterclockwise. And what this means is that when you render this, you can specify that the back faces, which are specified in clockwise order, will not get drawn. Of course, you can't see this because you only see the front faces. Yeah, so that's an optimization technique. And we can use this now to just render the backside of the model for the light perspective. And now we need to specify which face to cull. So we want to cull the front face, only draw the back face. And now when we actually render the scene, we want to cull the back face. And if we do this, what you can see now is that basically shadow acne is removed. It only appears on the backside of the faces. And this is very nice because the back face of our model like the back face, wait, how should I say it? So the back face has a diffuse lighting value of 0. So basically meaning not lit. So we can just mix the shadow factor into the intensity. And this way, the back face, this weird effect would be zeroed out. So we would multiply this by 0 if we multiply this by the intensity. So like this. And if we then rerun this, intensity, yeah. So wait, I need to multiply this with the diffuse lighting factor. I think. Yeah, so let's just use this for a second. So if we multiply this with the diffuse factor, we can see that, yeah, the back faces are black anyways because they are not in light. So the weird effect cannot be seen anymore. So what we can do basically is if we move this up here, we can just multiply the diffuse factor with the shadow factor. And this way it gets directly multiplied like here. And now we can use the actual intensity like previously. I did something wrong. Over here. So yeah. So that's shadow. Yeah, so that's basically it. Yeah, thanks. Okay. So what I actually wanted to do now is improve the quality of the shadow, because as you can see, when you look at this, it looks really bad. It looks like jagged and yeah, I mean, you can see the resolution of the light texture. And that's really I mean, it looks very bad. So what I wanted to do is improve the quality of the edges of the shadow so that they are smooth. But the problem is I already streamed like 3 hours. So I think I will do this in the next one. Or what do you think? What do you think, guys? Yeah. So maybe I can teaser what I wanted, how I wanted to improve this. So there is this method called PCF, which is percentage closer filtering. Yeah, okay. So it's your homework. So making, I actually found a method to improve the quality of the edges, which doesn't actually take that long to do, but I don't know, it would still probably take like half an hour. So there's one way you can just look into neighboring cells, so you can sample the texture like with a slight offset, and this way you get you can then get an average value of what the neighbors look like. So if you look at the texture, you can look at this depth, which is what we do now, but you can also look at these other depths here. And of course, you don't want to average the depths because that makes no sense. But basically, you perform this test for every of these points here, and then you average the resulting shadow factor. So if this was shadow 1, if this was if this was shadow, then it would be 0. If this was shadow, then no shadow, then it would be 1. And all of these 0 and 1s you average, and this way you get smoother shadows. And what I found in this real-time rendering book, what's it called? I think it's real-time rendering. Yeah, so this book here, so I have this book. It basically lists a bunch of, it's not like a tutorial, it just lists a bunch of techniques that can be used to render certain effects or something. And I found this, what I thought was quite a simple method, is just you kind of randomly rotate the samples in your, like, of course you use multiple samples, and then you place them a bit randomly and you rotate them a bit randomly, and then you get smooth shadows. So yeah, that's basically what I wanted to do, but it's a bit, the stream is a bit long, so yeah, I would say that's it for the stream. I hope it was understandable. But yeah. And I know my streaming frequency is not that high, but yeah. I don't know, I have to do a bit of stuff. Like, I'm not a full-time YouTuber or something. That's why I can't really make this more frequent. But yeah. Yeah, that's great to hear. And yeah, so thanks everyone for being here. And I would say until next time. Bye.